Welcome to Empowered Learning. This video will be about techniques of integration using the technique of trigonometric integrals. So in this video, we are going to learn how do we deal with taking the most general antiderivative of sine raised to some power, cosine raised to some power, and a mixture of sine and cosine being multiplied times each other raised to a power. And we're also going to deal with tangent and secant being multiplied times each other, and both of those raised to some power. And we're also going to be dealing with some integrals where we'll have to use some trigonometric identities here, mainly our product to sum or sum to product identities, to be able to rewrite these last three into a form to where we can actually take the antiderivative of it. Okay. So that is the focus for today's discussion here on this video. We will start off with this these first two kinds here, which is just sine raised to a power, cosine raised to a power. And of course, we want to look at instances where cosine and sine are raised to a power of 3 or higher. And so part of the reason for that is we know that sine squared of x and cosine squared of x actually have a trigonometric identity via the reduction formula. And so we could easily rewrite those two functions in terms of something else that we can integrate relatively easy. But it's when we get higher than that we have to do a little more work and be a little bit more creative. So our strategy for dealing with taking the indefinite integral of sine raised to the 3 or cosine raised to the 3 or higher is basically what we want to do is identify if we're dealing with a power that is even or odd. Okay. And so there's a lot of different rules here with all that, but I'm going to try to make it as simple as possible. I am going to run through what those rules are, but then afterwards I'm going to give you some examples so that you can get a feel for how it works. It's not necessary for you to remember the rules, but it is necessary for you to know what it is that you're after. Okay. So in the instance to where this power for sine is going to be odd, and I'm expressing it as m is equal to 2k plus 1, but essentially is going to be odd, then in that case, what we would want to do is take this particular expression here and just basically break it out to where we have an extra sign hanging out here. Okay. Of course, if it's cosine, kind of the same thing. We want an extra cosine hanging out there. Now, for this portion, we want to rewrite the rest of this as sine squared raised to some power, because of the fact that we know that sine squared is the same as 1 minus cosine squared. And here we want to rewrite the rest of this as cosine squared raised to some power, because we know cosine squared is the same as 1 minus sine squared. Okay. So when we do that, and that's what this step 2 here says, when we do that, we have a situation here where if we replace sine squared with 1 minus cosine squared and cosine squared with 1 minus sine squared, then we can essentially just use substitution. Okay. And again, I'm not going to go into all the gory details on that now, but I will show examples. All right, so we've talked about how to deal with sine raised to some power and cosine raised to some power whenever that power is odd, but we haven't talked about what to do when it's even. Okay, if it's an even power, meaning like sine raised to the 4 or sine raised to the 6, or let's say cosine raised to the 8 or cosine raised to the 10, then from there what we want to do is again just rewrite it as in groups of sine squared, basically. Okay, so like cosine raised to the 8, we would have cosine raised to the 8. We could just express this as cosine squared, all that raised to the 4. Okay, now once we do that, then we just use our reduction formula for either sine squared or cosine squared, depending upon the one that we're having to deal with here. And of course, our reduction formulas for sine squared, we know that that's going to be 1 minus cosine of 2x all over 2. And for cosine squared is going to be 1 plus 2x all over 2. And of course, we use those to be able to rewrite this. And once we do that, then of course, whatever this power is, we would just take whatever this expression is and of course multiply whatever this expression is times itself that many times. After that's done, then of course we'll have to kind of rearrange things, see what we have, and we may have to repeat the process on some of these until we get something for each term to where we can actually take the antiderivative of it. Okay, and so that's why I say a lot of times there's no need to go into the gory details, because a lot of times it ends up just being different. So you just kind of got to take, hey, this is how I get started, and then just kind of take it from there. So as an example here, if we had cosine raised to the 5, then what we would want to do here is rewrite cosine raised to the 5 as just cosine raised to the 4 times cosine, but write cosine raised to the 4 as cosine squared of x squared. And then, of course, from here, we would recognize that cosine squared is the same as 1 minus sine squared. And then from this point, we would essentially say that we would want to let our u substitution be sine of x. So here if we say let u equal sine of x, then of course that would imply that du is going to be cosine of x dx. And therefore we know that cosine of x raised to the 5 could just be rewritten as 1 minus u squared, all that squared, because again u is just sine. And then here we would have this cosine x dx, and we would just write this as du here. And I know that we don't have a dx here, but whenever we would integrate this, of course we would have the dx out here like this. Okay, so we would have all this going on here, and then of course that's where the dx part will come from, and we'll just say cosine of x dx, all that's just equal to du. And so now what we would have to be faced with here is just integrating essentially this polynomial here. Okay, and of course that's a lot easier to deal with than trying to integrate what we started off with. And so that's basically how we go about attacking these kind of problems. So for another example, let's look at a case where we have to deal with an even power that's higher than 3. So in this case, we know that sine raised to the 4 is just the same as sine squared, all that squared. Okay. And if you remember before, we know that via the reduction formula, we know that sine squared of x is going to be 1 minus cosine of 2x, all that divided by 2. So we could rewrite this as just 1 minus cosine of 2x, all that divided by 2, quantity squared. And note that there is an understood 1/2 that's in here. So if we want to, I'm going to rewrite this another way. We could actually write this as just 1/2 times 1 minus cosine of 2x. Okay. And so if we do that, we know via exponential properties, 1/2 squared would be 1/4. And of course we would have 1 minus cosine of 2x quantity squared here. And of course, from that, we would just multiply out the 1 minus cosine of 2x quantity squared. And if we do that, we'll get 1 minus 2 times cosine of 2x plus cosine squared of 2x. Okay. And so from here, we know that this 1/4 is fine. We know the 1 is fine. We know that we can take the antiderivative of 2 times cosine of 2x just fine. But here we have this cosine squared of 2x that we still can't take the antiderivative of straight up. So we need to use our reduction formula again. And of course, cosine squared of x is going to be 1 plus cosine of 2x, all that divided by 2. And notice here that since your argument is 2x, then that would be 2x here for the cosine square part, which would mean we would have 1 plus cosine of 4x here. So we would rewrite all of this, and then for that last term there, this would be just 1/2 times 1 plus cosine of 4x. Okay. And so now that we have all that, then at this point, of course, we can multiply the 1/4 through if we wanted to, but each and every term that we're dealing with from this point forward, the 1 we can take the antiderivative of easy, the 2 times cosine of 2x we can take the antiderivative of easy, and this 1 plus cosine of 4x we can take the antiderivative of that easy. Okay. So what we'll do now that you've kind of seen some examples of how this works, we'll go through a few examples, from beginning to end. And then after that, I will make another video for the next type that we're going to do, which is the products of powers of sine and cosine. Okay, so for this first example, I've already worked it out, and we see that we have a definite integral here. What we're working on looks very similar to what we just got through talking about, and that was one of the reasons why I did it. So notice here that the only difference is now that we have sine of 3x raised to the 4 instead of just sine of x raised to the 4. Okay, so what we did here is going to look very similar to what we need to do in this problem that we're about to go over. So you see how we start off by rewriting sine of 3t raised to the 4 as sine squared of 3t squared. Okay, and then of course we use the reduction formula again for sine squared, and that'll just be 1 minus cosine of 2 times whatever the argument is, which is 3t in this case, all that divided by 2, and then we take that whole entire expression and square it. Okay, so we do that. Of course, we realize that 2 times 3t is just 6t. We know that there is an understood 1/2 that is out here times the 1 minus cosine of 6t. We square that. Of course, 1/2 squared is going to be 1/4, and 1 minus cosine of 6t is going to be 1 minus 2 times cosine of 6t plus cosine squared of 6t. And then, of course, like how I said in the previous example, we just need to rewrite what cosine squared of 6t is using the reduction formula again. So you can see down here, I'm kind of rewriting everything and just noting to myself, hey, I need to rewrite this using the reduction formula. So I come down here and I first do substitution here. I don't necessarily have to do this, but this is the way I went about doing it when I worked this out. So I want to make this look like something simple. So I'm putting everything in terms of theta. So in here, I'm just showing you how we actually get that reduction formula here. It actually comes from knowing the cosine of 2 theta, which you could also say cosine of theta plus theta. If we use that, the addition formulas for cosine, we could actually back our way into coming up with this formula here. So that's what this step is. And then from there, we know that we just have cosine squared of theta now. And let's see here. Yeah, I should have replaced everything in terms. Well, yeah, I should have replaced everything in terms of theta here, but I didn't actually use it for substitution. I just did it to kind of make it look a little easier. So once we're here, again, I'm just rewriting this, the cosine squared of theta. And then once I have it rewritten in the way that I want it, which is here, I go ahead and substitute in theta to be 6t. Okay. So again, not necessary to do that, but I know some people need to actually see those in between steps, so that's why I did it. And so, of course, from here, everything now is in t, and I can take the antiderivative of cosine of 12t with no problem. Technically, we do need substitution again, but this is one of those integrals, if you're watching this particular video, that you've probably done it so often that you know that the antiderivative is just going to be sine of 12t divided by whatever this number is, which is 12. Okay. And of course, I actually show those steps there. And since we're dealing with a definite integral, I'll also go ahead and rewrite my limits of integration from being in terms of t to being in terms of u. So that's what this step and this step is all about. So once we're there, then we take what we have in terms of t and doing some splitting of the integrals here. And then now I have everything written in terms of u for this first one, because that was the one where I really needed it. I can keep this second one here in terms of t because it's not going to hurt anything. And then the rest of this is just me taking the antiderivative of this integral here and this one. And then the rest of this is just kind of working everything out. Okay. So once I actually work it out, do the net change theorem and substitute in 12 pi minus, and then do the same thing, substitute in 0. I see that my final answer here just ends up being pi over 2. So going back to where we were here, once I got to this point, I now know what this particular integral is. Okay. And so all I need to do now is work on what these two integrals are just going to end up being, and then of course multiply my 1/4 through, and I will have my final answer there. Okay. So we'll kind of move forward here. So now that we know this information, we get back to our original problem, which was this. And we had these three integrals. This one, we've already found out what the answer to it is. Of course, minus save the 1/4 here. We'll multiply that in later. But now we need to figure out what this integral and that definite integral will be. And of course, the antiderivative of any constant is just that constant times the variable, which is t. Evaluate that from 0 to pi. And the antiderivative of cosine of 6t will just be sine of 6t, all that divided by 6. Okay. And of course, I've done substitution here, but you see that it ends up actually being that, and this 1/6 and the 1/2 multiply together to be 1/12. So I'll pull that outside, and now just dealt with sine of u. And again, I did that knowing that here I could use u to be 6t. Okay. So once that's done, then of course we just do all the work to finish everything out, and we see that this answer just ends up being 3/8. So what we'll do now is actually work one from beginning to end that's not worked out, so that we can get a feel for how to do this. All right, so for this example, what we want to do to start out, since we have the square root of x in here, is let's start off using some kind of substitution to make this look a little easy, okay? So we'll start off here by saying let W equal x raised to the 1/2, which is, of course, the same thing as square root of x, okay? So if we do that, then we know that the derivative of W with respect to x is just going to be 1/2 x raised to the negative 1/2. And we could rearrange this here so that we could solve for what x raised to the negative 1/2 dx is going to be. And we know that because we see we have a x raised to the negative 1/2 here, dx here that we want to replace. So if we want to do that, we just do some rearranging, multiply both sides by 2, as well as multiply both sides by dx. And we see here that 2dw will just be the same thing as x raised to the negative 1/2 dx. So therefore, we know that sine cubed of square root of x divided by square root of x here, which is the same as this x raised to the negative 1/2 sine cubed of x raised to the positive 1/2. All that is just going to be have sine cubed of w. Pin slide in there. So sine cubed of w, and in place of the x raised to the negative 1/2 dx, we have 2 times dw, okay, which essentially just ends up being this. So now we need to deal with the sine cubed part. So here we note that sine cubed, because it's odd, we want to break this out to where we have an extra sine of w just hanging out there. Okay, so we want this by itself. And the reason for that is that in this form, we know that sine squared is the same as 1 minus cosine squared. And now that we have it in this form, what we can do is use substitution again, but we're going to say let u equal cosine of w. And that's going to imply that du is equal to minus sine of w dw. Okay. Thus, here, we'll say that minus du is going to be equal to sine of w dw. Okay. And so just to kind of round everything out here, I didn't put this in before, but I'll go ahead and put it in now. I'll just go ahead and write it in like this. So I didn't put in that dw that's here, but if we want to be technical about it, we should have the dw in like that, which means here we're going to have a dw here, which means we're going to have a dw here. Okay. And so now we see that all of this is just another way of saying negative du. And of course, what we have here is just another way of saying 1 minus u squared. And so now we could take what the new form of our integral is and finish up. I'm going to draw an arrow down here to signify that we're going to finish up using that. Got sine cubed dw. This is just going to be 2 times integral. We can replace this with just 1 minus u squared du. And since that's a negative on that, we're going to pull that out in front of the -2. And then from here, we take the antiderivative of 1 with respect to u. It's just u. Take the antiderivative of u squared with respect to u. It's just going to be 1/3 u cubed. And plus c, since we're taking the most general antiderivative. And from here, all we need to do now is back substitution to get our final answer. Okay. So from here, we know that our u was actually cosine of w. So this will be 2 cosine of w minus 1/3 of cosine cubed of w plus c. And then finally, w, if we go back, remember w was equal to square root of x. So our final answer is going to be a minus 2 times cosine of square root of x minus 1/3 cosine cubed of square root of x. All that plus c. And of course, from here, if you want to, it's not necessary, but I'll go ahead and do it here. You can go ahead and multiply the -2 through to both terms. And you'll end up getting what I'm writing here, which is -2 cosine of square root of x plus 2/3 cosine cubed of square root of x plus c. All right, so this concludes the examples on dealing with integrals to where we have powers of sine or cosine that are 3 or higher. So the next video that I'm going to do, which will be the part 2 video for this series, we're actually going to deal with integrals to where we have the product of sine and cosine with powers that are going to be 3 or higher for each of them.